Okay guys, welcome to the application of basically what we learned last unit over function relationship. So today is what we call optimization, and what you have in front of you is a graph of, well actually it's two graphs of a revenue versus cost analysis. Basically the overall goal is to look at profit of any random company. So any company in general is trying to maximize their profit. And by doing that, they have to look at both their revenue versus their cost. So if you look at this graph, revenue is in blue, cost is in red. Revenue is a linear equation that's constantly going up, which one would think that we always want that. We always want our revenue to go up. However, if you look at your costs aren't quite so linear. For a little while at the beginning of the graph, your costs are actually higher than your revenue, which means you're operating at a loss. At some point they come together, so you're breaking even, and then eventually you get to that sweet spot where your revenue is higher than your cost and you're reaching your maximum profit. Because remember, profit is revenue minus cost, okay? But companies are like, oh, I want to get more and more revenue. So as their revenue increases, however, their cost is also increasing. So there's always that fine line of like, well, how much more revenue do we need versus our cost? Are we actually making money here? So companies look at this kind of stuff all the time. They take all kinds of analysis and they basically are trying to optimize their profit. So what we're talking about today is different situations where we are optimizing a specific idea or concept using the information about functions that we've done over the past couple weeks. So this first problem is we are finding maximum volume. So a manufacturer wants to design an open box having a square base and a surface area of 108 square inches, as shown in this figure. What dimensions will produce a box with maximum volume? So when you're working this kind of a question, you want to first recognize, what are we trying to maximize? And in this case, we are maximizing volume of a rectangular box, okay? Square box, okay? Whenever we maximize anything, okay, think back to last unit, okay? How did we find the maximums or minimums of a function? We had to look at our derivatives. And then we looked at the derivatives, and we can either use, we could use one of three tests essentially to find the actual maximum and minimum values. You could use the candidates test. You could have used first derivative test, or even the second derivative test. Now, with candidates test, you're looking at all of the critical numbers and the endpoints. Okay, first derivative test and the second derivative test. Now, I know technically we have used those to look at relative extrema, but if you only have one relative extrema within a certain interval, then you can also use these first and second derivative tests to justify that a relative extrema is also an absolute extrema. Okay, so whenever we're working these today, we're going to kind of rotate between candidates, first and second derivative tests. Sometimes we'll do one, sometimes we'll do all three. It just kind of depends on the situation and pretty much how I'm feeling at the time. So we are trying to maximize our volume using derivatives in one of those three tests. So the first thing we need to do is come up with an equation for volume in relation to the question at hand. So this is a square box, or an open box with a square base. So the volume is usually length times width times height, but our length and our width are going to be the same. So the volume is going to be x squared times your height. This is the function that we are trying to maximize. However, everything we have done up to this point, we only have things in terms of one variable, okay? Or really, I guess we should say volume can be written in terms of one variable, okay? So here, volume is written in terms of two variables, both the x here and then also its height. So in order to get this to a place where we can actually maximize it, what we need to do is to put into terms of one variable. And in this case, I would probably opt for putting everything in terms of x just because that's what we're most familiar with. Okay, but everything's in terms in single variable, in this case x. Okay, well, in order for us to do that, we need to know a little bit more information. So they at least told us within the context of the problem that they want to design the box that has a surface area of 108 square inches. So I can use that based on the box diagram that I have, and maybe I can come up with an equation for h in terms of x, so I can use that in this over here. So we're going to use Suze. I don't know who Suze is. We're going to use the fact that our surface area is equal to 108, 108 square inches to get h in terms of x. Okay, so our formula for surface area, 108, is equal to, we have the square base on the bottom, so that's going to just be x squared plus, we have 4 sides of dimensions x by h, so 4xh. And again, it's an open box, so there's no top piece, so we don't have to worry about having 2 x squared pieces, okay? So my surface area is x squared plus 4xh. And so the whole point of this is to get h by itself. So h is in terms of x, so I can use that up here, okay? So 108 minus x squared equals 4xh, divide by that 4x, and so 108 minus x squared over 4x equals h. So now I have h in terms of x, and I can plug that into my volume, okay? So if it helps, now I can write volume as a function of x. So remember how we've done f of x in the past instead of y? Well, now we're using v of x to show that my volume is a function of x. So volume is x squared, and instead of h, I'm going to use this new piece that I found over here and say 108 minus x squared over 4x. Okay, I'm going to basically plug this in right there. Okay, and then let's see if we can clean that up a little bit here. Let me scroll down. So my volume is going to be, one of these x's will cancel out with that x right here. So then I'd have 108x minus x cubed all over 4, which I could leave it like this, or if I wanted to, I could also make this volume is equal to, the 108 over 4 is 27x minus x cubed over 4. Okay, this is my function, volume as a function of x, because now that I have this as a function that I know how to work with, I can manipulate it and do like the derivative and find critical numbers, and then find relative extrema based on that, and then continue to go from there to find the optimal volume for my, or the optimal dimensions to provide the maximum volume for my box, okay? So again, we had 3 different ways to do this. We talked about earlier, Canada's test, first derivative test, and second derivative test. For this one, I'm going to go ahead and use our Canada's test. Get a little room here. So let's use Canada's test. Okay, so if I were to use the Canada's test, I need to first find my critical numbers of my volume function. So to do that, I need to take the derivative. So let's see, finding critical numbers, I'm going to say volume prime is going to be 27 minus 3x squared over 4, okay? Or 3/4 x squared. Either way you want to write that. So I need to take that and set that equal to 0. So 0 is equal to 27 minus 3x squared over 4. So I'm going to move that over. 3x squared over 4 is 27. Cross multiply and divide. Multiply by 27 at the same time, divide by 3. So x squared is equal to, actually it's probably easier to divide by 3 than multiply by 4. Either way, you get 36. Okay, so x is equal to plus or minus 6. So that's the actual solution. But we need to think about, in context of this problem, what would actually legitimately make the most sense. Okay, so could I have a box dimension size of -6? No. Box dimensions, or just dimensions in general of anything that is a concrete thing, has to be positive, okay? So we're only going to keep x equals 6 as our critical number. Okay, I need to also look for where my volume is undefined. Or I'm sorry, the derivative of my volume is undefined. Well, this equation itself is a quadratic equation. There is no place where this function is undefined, so this is none. Okay, so my only critical number here is going to be 6. Okay, so I found my critical number, and it's 6. So to use candidates test, we need endpoints, okay? So we need to think about the box itself, okay? What are the smallest sizes, what is the smallest dimension it could possibly be for x versus the largest dimension that it could possibly be, okay? So the absolute smallest it could be would be 0, because if you got any smaller than that, you wouldn't actually have a box, okay? So candidates. Okay, so we're going to have our x and our volume of x, okay, because we're trying to maximize volume. So 0 is my smallest potential dimension size for one side, because otherwise I wouldn't have a box. 6 was my next number, okay, my critical number. I need to figure out what's my other endpoint right here. Like, what could I really just go to an infinite sized box? Would that make any sense? Well, no, not really, because if your box was infinitely large, you wouldn't fit the surface area of only 108 square inches, okay? So I need to use that 108 square inches to come up with my endpoint essentially, okay? So if my surface area was x squared plus 4xh, which was 108, okay? If we're thinking about the box here in general, like, let's say you had 0 for your height, okay? Your height was the smallest it could possibly be, and so it basically just means you have a flat piece of cardboard. Okay, well, if you have a flat piece of cardboard, then essentially that's the biggest values for x that you can possibly get, because the bigger your h is, the smaller your x's get, because you got to take space from somewhere, okay? So if I were to assume that h was equal to 0, that means my largest possible value for x would be when x squared gives me that exact 108. So then x is equal to plus and minus root 108, which is square root of 108. Simplified down, you don't have to simplify that, you know how I feel about that, but if you wanted to simplify that, that would be 6 root 3. Okay, because 36 times 3 is 108. There you go. So the reason why it's nice to write that as 6 root 3 is that it's easier to identify that that is the maximum possible value of my, that's the maximum possible value of my x values, okay? So now I have my actual table, and I can go ahead and figure out what are the maximum volumes that I could have, or what are the possible volumes that I could have. So volume, remember, was equal to this, what's up there? 27 x minus x cubed over 4. Well, if I plug in a 0, well, my dimension would be 0. That's unfortunate, but it is what it is. When you plug in a 6, you end up with a volume of exactly 108. But then when you plug in that root 108 or 6 root 3, you end up with a volume of 0. And this makes sense because here, all of your volume would be coming from just your flat piece of cardboard, which that's a two-dimensional piece, and so two-dimensional objects have no volume, okay? So my maximum volume occurs right here, okay? But that's not what they're asking. They're asking for the overall dimensions, okay? So this is where it occurs, okay? So if my dimensions, if x is 6, well, the dimensions of my box are x by x by h, okay? So x by x by h has to give me my maximum volume. So I need to figure out what is h equal to? Well, we already had an equation for h earlier. Remember, h was equal to that 108 minus x squared over 4x. That was what h was. So h is equal to 108 minus 6 squared over 4 times 6. So h is equal to 108 minus 36 over 24, 72 over 24, so that works out to be a 3. Okay, so then my dimensions to produce maximum volume are 6 by 6 inches by 3 inches. Okay, so this was how we optimized this question using the candidates test. Now, if I wanted to, I could have used the first derivative or the second derivative test. Luckily, I only had one critical number over the possible domain of my function. So what I would need to do is look to see where my derivative changed signs. Hopefully, it would change from positive to negative to match the fact that I had maximum volume here. And then again, if I did the second derivative test, I would plug in my critical number of 6 into my second derivative, and I would get a negative second derivative, which would imply that my function was concave down, which would imply that it was a relative maximum, but because it's the only possible maximum in the possible domain, that must justify it as the absolute maximum. Okay, on Canvas, I have a filled-in version showing you how you would write that using first and second derivative test. I'm going to go ahead and just go to the next question here for the sake of time, but you are welcome to check that out so that way you can see exactly how I have done that in the past. Okay, so some quick guidelines to help you with optimization of how to work these questions. Okay, the very first thing you're always going to want to do is identify all the quantities and all that you're given and all the quantities that you have to determine. So the last question, we were given a surface area, we were trying to determine the dimensions that gave us a maximum volume. So that's always the first thing you need to start with. Okay. Step 2, write an equation for the quantity to be determined. The last problem, we needed to write the equation for volume, which we did. And then you need to get that into one single variable, which may require use of a second equation from the given info. We had to rewrite volume in terms of x specifically, and so we used our surface area to eliminate h whenever we plugged it back into our volume. And then determine a feasible domain for the original equation, which we did. Our feasible domain for the last one was from 0 to 6 root 3. And then find the minimums and maximums using the candidates first or second derivative tests. Again, we use the candidates test on the last question, but first and second derivative tests are helpful, and I have that shown on Canvas. And then I also, on this next question, I think we're going to do the first derivative test, so that way you can see how that one would work, but for a different problem. Okay? So, finding minimum distance. Which points on the graph of y equals 4 minus x squared are closest to the point 0, 2? So here's the curve, 4 minus x squared. I want to know what point anywhere along this curve are closest to the point 0, 2. Okay, so our goal is that we are trying to minimize distance. Okay, so we want to find the minimum distance between 2 points here. Okay, so find the minimized distance between a function and a point. Okay, well, so we need to think about step 1. Okay, done. We identified the quantity. We need to write an equation to be determined here. So the equation that we would write here would be, if we're trying to minimize distance, would be our distance formula. Think back to, oh gosh, I think you did distance formula in geometry. Was the first time you did distance formula? I can't remember. It's been a little while. But I think you guys did that in geometry. So you're going to have x2 minus x1 squared plus y2 minus y1 quantity squared. So I'm trying to minimize this function here, or this equation, but right now it's not really a function because I have too many variables involved. Okay, so this is actually distance between two specific points, but luckily I already at least know one of the points. I know that I'm working with the point 0, 2, so I'm going to go ahead and plug that in for x1 and y1 because that's the first point that I'm working with. So my distance is equal to x2 minus 0 squared plus y2 minus 2 squared. So it's cleaned up a little bit. We still have too many variables. And x2 and y2, I'm going to go ahead and just make that x and y, because I'm going to find an x and y coordinate somewhere on this whole curve. Okay, so we're getting closer, but again, we still need to write this. This thing needs to be in terms of one specific variable. Okay, so I want to write my distance as a function of just x or just y. Okay, now luckily we already have an equation. Maybe you see it somewhere. Actually, it's written twice on your paper, or on this set of notes. It's written twice on there where we have one function already written in terms of the other. Does anyone see it? I'll give you a hint. One of them is highlighted in blue. Ding, ding, ding. Right here. I already know that y is equal to 4 minus x squared. So where I have a y right here, I'm going to rewrite that as 4 minus x squared. So now I can write my distance as a function of x and say that I have, well, x minus 0 squared, I'm just going to make that x squared, plus, instead of y, I'm going to write 4 minus x squared, 4 minus x squared minus 2 quantity squared. Clean this up a little bit more, and I've got the distance is equal to the square root of x squared plus 4 minus 2, so 2 minus x squared quantity squared. Okay, so now my distance is written as a function of just x. Okay, but that's what we are going to have to maximize. I'm sorry, not maximize, minimize in this case. So I've got it in terms of one variable. Oops, there we go. Let's see, I need to erase that little guy. Okay, so boop, 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 in terms of one variable. Now, minimize. And how do we minimize? We take the derivative. Although the derivative of this is going to be quite the chain rule situation here, which I'm okay with, but I'm going to see if there's a way, instead of making a chain within a chain, I'm going to kind of clean up just the inside a little bit, so I just have this inside the radical for my chain rule. So I'm going to say the distance is equal to x squared plus, I'm going to go ahead and apply FOIL here, so 4 minus 4x squared plus x the fourth. Okay, and then I can combine that over here, so dx is equal to square root of x squared minus 4x squared. But I'm going to go ahead and try to write these in degree order here, because I know everybody tends to like that a little bit better. So x to the fourth minus 3x squared plus 4. Okay, so that is my equation for my distance, which I could also, in terms of helping me take the derivative here in a second, x to the fourth minus 3x squared plus 4 to the 1/2. Okay, now I can minimize. So maybe, now minimize. Okay, so to minimize this, d prime of x, I've got 1/2 x to the fourth minus 3x squared plus 4 to the negative 1/2 times the derivative of the inside, which is going to be 4x cubed minus 6x. Okay, so I have taken the derivative, and I now have the derivative of distance. Okay, I'm going to see if I can clean that up a little bit here. This 1/2 will reduce both of these terms here, so make that 2x cubed minus 3x all over square root of x to the 4 minus 3x squared plus 4, or you could leave that to the 1/2. Either way is perfectly fine. Okay, okay, so I've taken the derivative. Now I need to find critical numbers. Okay, so now finding my critical numbers. So I need to set the top equal to 0. So d prime of x equals 0. So 0 equals 2x cubed minus 3x. So I can take out an x. Well, the 2x squared minus 3. And then I've got, so x is equal to 0, or x squared is equal to 3/2. So x is equal to plus and minus the square root of 3/2. Again, you can always rationalize that if you want to. Nah, you know me. I don't feel the need to do that sometimes. D prime of x is undefined. Ooh, we do have a denominator for d prime. So whenever this is equal to 0, that's going to give me a problem. Also, I can't put a negative number in here, but I don't think we would end up with a negative in any way here. So I think we're good to check with that. We just need to make sure that this is equal to, where this would be equal to 0. So x to the 4th minus 3x squared plus 4 equals 0. We're going to factor this somewhat like we normally do, but instead of x squared here, I have x to the 4th, but that's fine. You're just going to make this x squared minus 4x squared plus 1. Does that work out? Let's see. Yeah, I think so. X squared minus 4 and x. Let's see here. So x plus 2, x minus 2, and then that has no real solution. So then x is equal to plus or minus 2. However, if we did that, let me see something for a second. Wait a minute. I can't factor. I mean, I can. I just didn't at this point. You can't factor this. That was silly. Silly, Miss Murphy. Let me erase that real quick. Because this is a positive, the signs for these two terms must be positive. Ah, what a rookie mistake. That's okay. We all make them. We erase and we move on. But luckily, the nice thing is this, I could go ahead and, I know I can't factor it. If I plug this into the quadratic formula, the only thing I need to check is that b squared minus 4ac. So b squared, so 3 squared minus 4 times a times c. So this is going to be 9 minus 16 root negative 7. So this tells me there are no real solutions. Okay, which is good. So that means there's no critical numbers from my denominator equals 0. We're safe here, guys. Whew, that was a close one. Sorry about that. Okay, so now we need to come up with a reasonable domain. Well, if we look up at the problem again, most likely I'm going to say that it's somewhere in here would be the 2 points that are closest, because basically it's hard for me to visualize for sure where this is the closest, but I don't know where it starts to be like the furthest away. But I'm fairly confident that we won't go any further than -2 or +2. If you wanted to go ahead and use negative to positive infinity as your possible domain, you probably could here, but it's not really necessary, because if you get any further than this, you are way outside of the possibilities of points that would be a minimum distance away from the point 0, 2 on that curve. So my critical numbers were 0 plus or minus root 3/2, and I'm only going to go from -2 to +2 in my possible domain. So here we go. We're going to say, all right, so, and I said that we were going to use the first derivative test here. So I'm making a chart. So this one is first derivative test. Okay, I'm looking for my minimums and maximums to see which one's the furthest, which one is the closest to my point. So -2 is where I'm stopping. -2 to negative root 3/2. What is happening at negative root 3/2? I know that my derivative is 0 here. Negative root 3/2, comma 0, 0. Oops, I almost wrote infinity. All right, 2. Actually, I'm going to just put stop. Okay, and again, we are looking strictly at our derivative. Okay, I know that my derivative is equal to 0 here, here. Oh, I didn't put a I will fix that. Boom, done. Okay. Oh, and it was also 0 there. So now I just need to figure out what is happening here, 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 and here. Okay. So let's see. So the square root of -3/2. I'm going to use my handy calculator real quick and tell you that the square root of 3/2 is 1.2. So then I'm going to go ahead and use like -1.5. Okay, so f prime of -1.5. Okay, plug that into my derivative. Yeah, this might come in handy to type that into a calculator. I'm not gonna lie, that's kind of a gross number. Well, the nice thing is you know that you only have a positive number down here. Okay. Because if not, it wouldn't exist. So you know that the denominator is going to be a positive. Okay, so then we just need to worry about the numerator. So the numerator, 2x cubed minus 3x, I'm just going to go ahead and type that in, and I find that when I plug in -1.5 into my denominator, so I plugged -1.5 into my calculator, boop, boop, and I discovered that this would be less than 0, so I have a negative here. Let me scoot this down, or up a little bit, give you all some more visual here. If I plugged in a number between that, I'm going to plug in, oh, I wrote f prime. Ooh, we're not working with f right now. What are we working with? D prime. So D prime. That gets confusing. My bad. Okay, so D prime. Oh, let's go with -1. That's a little bit easier to work with. And you plug in D prime of -1, you end up with a positive number. Let's go with D prime of +1. And now the nice thing is this is an even function here. So whatever you get on the, well, no, just kidding. Scratch what I said. I read something, whatever. Okay. D prime of +1 is going to also be negative, while D prime of something bigger than that, like let's say 1.5, is going to be positive. Okay, so I am trying to find the minimum distance, right? Yes, no? So I want to look for where my minimums occur. Okay, so my minimums occur where my derivative changes from negative to positive. So that's going to occur here, and it occurs here. Now, I'm aware that 0 is a critical number, but it's also a relative maximum because my derivative changes from positive to negative. So we actually ignore that. We only want relative minimums, okay? So then we know that we have a relative minimum at x equals plus or minus √3/2 because D prime at both of those is equal to 0 and changes from negative to positive. Okay, but we want to find the absolute minimums, okay? So, or we want to find the absolute minimum distance. Well, these are the only two minimums that I have. So let's go ahead and find the minimum distance for each one. And then one of them maybe would be the absolute and one of them would just be a relative, okay? So when I plug this number into the distance formula, the square root of 3/2, I'll just go ahead and show you this fancy math here and tell you that the minimum distance from y equals 4 minus x squared to two random points occurs at points square root 3/2 and 5/2 and negative root 3/2 comma positive 5/2 as well. So what we did was I knew that, well, I didn't necessarily need to find the minimum. Well, okay, so I found the locations that give me the relative minimum distance, okay? I could plug that in to my original y equals 4 minus x squared to get the coordinates here. And here's the deal. The reason I did that is because 4 minus x squared is an even function. So 4 minus x squared. So whatever distance you have on one side, it's going to be the same as the distance on the other side of like the negative versus the odd version of the x value. So they both give you the exact same distance. It's just that it occurs in two different places. Okay. So those 2 points will be the same distance away from 2. So since, oh, wow, sometimes my computer does that. Since y equals 4 minus x squared is an even function, the distance from 0 to, wow, to either point above will be the same. Okay, so I hope that makes sense. That was using the first derivative test to find minimum distance. Okay, so there are a handful more actually there's only a couple more problems that are on the slideshow, so that I'm going to post on Canvas. Again, I've given you 2 really good examples. I feel like that's a pretty good intro. That way the video doesn't get too long and gives you some time to practice. Practice them on your own, and then come back to the video, see if you got the same thing that I got, or come back to the Canvas page where it's all filled in and make sure you got the same answer. Also, 2 of the last 2 questions on there are going to give you like, here, I'll go ahead and show you real quick. So I'm going to skip this one and this one for now. Do you see where it says 1990 BC3? So this is the actual question from the BC exam in 1990. So if you just type in 1990 BC3 into Google, obviously try the question first, okay, on your own. But then if you want the actual answer, go ahead and just type in 1990 BC3 into Google, and it'll pop up the solution for you. But I'm not going to have time to go through all of these today, and that's okay. You are capable of doing this all by yourself, and I have full faith in you guys. I really do. As always, Khan Academy, Prof. Rob Bob, textbook for help. Okay.